Right now, in this moment, as you're listening to this, you're probably lying down. Maybe the lights are off or nearly off. The room is quiet. Everything around you feels completely, deeply still. And that feeling makes total sense. Your body is not moving, the floor is not moving, the walls are not moving. As far as your senses are concerned, you are completely, perfectly at rest. But I'm going to tell you something tonight that is going to permanently change the way you experience that stillness. You are not at rest. Not even slightly. Right now, this exact moment, you are traveling at over 1 million miles per hour. And I don't mean that in some poetic, metaphorical way. I don't mean it in the sense of time is flying or life moves fast. I mean it in the precise, measurable, physics textbook definition of the word. You are physically moving through space at a speed so extraordinary that if you could somehow feel it, it would be incomprehensible. But you can't feel it. And by the time this episode is over, you're going to understand exactly why. Tonight, we're going to peel back the layers of this invisible motion one by one. We'll start with the ground beneath your feet and work our way all the way out to the edge of the observable universe. We'll talk about the physics of why you can't feel any of this. We'll explore where the universe is actually taking us. And we'll sit with what it all means. So get comfortable. Close your eyes if you want. Let your body sink into wherever you're resting. And let me take you on the most extraordinary journey you'll never feel. Before we continue, make sure to like and subscribe if you enjoy relaxing science documentaries and fascinating journeys through the universe. Before we get into the actual speeds, we need to spend a moment on something fundamental. Why do you feel still? Your senses, your eyes, your ears, the receptors in your skin and muscles, they are not designed to detect absolute motion. They're designed to detect relative motion. The difference is everything. Relative motion means movement compared to your immediate surroundings. If everything near you is moving at the same speed in the same direction, your senses register zero motion. None. Complete stillness. You've experienced this before in a very familiar way. Think about the last time you were on an airplane at cruising altitude. 35,000 feet up, traveling at 575 miles per hour. Now think about what that felt like. Did you feel the speed? Did the air rush past you? Did your body press against your seat? No, you probably felt completely still. Maybe a little bored. You could read a book, drink a cup of coffee, fall asleep. That's because everything around you, the air in the cabin, the seats, the floor, the other passengers, the coffee in your cup, was all moving with you at the same speed. Your senses had nothing to compare against. So they reported, still, now scale that up, way up. The Earth is moving, fast, incredibly, almost incomprehensibly fast. But the ground is moving, the air is moving. The buildings, the trees, the oceans, everything on the surface of this planet is moving together as one unified system. Your senses have nothing to compare against. So they report, still. This is a principle that has been understood for centuries. Galileo wrote about it in the 1600s. If you're inside a sealed room, moving at a constant speed in a straight line, there is no experiment, no measurement, no sensation that can tell you whether you're moving or standing still. Einstein later built an entire framework of physics, the theory of relativity, on this same foundational idea. Motion is relative. What you feel is not speed, it's changes in speed. Acceleration. And the motions we're about to discuss? They produce accelerations so incredibly small that your nervous system cannot detect them, not even in principle. But that doesn't mean they aren't real. They are profoundly, measurably, cosmically real. Let's start at the beginning. The first layer of motion is the one most people have heard of, even if they've never really sat with it. The Earth is rotating on its axis. Right now, beneath you, the planet is spinning like an enormous top, completing one full rotation every 23 hours, 56 minutes, and 4 seconds. That precise duration is called a sidereal day, slightly shorter than the 24-hour clock day we use, because the Earth is also orbiting the Sun, which shifts the Sun's apparent position just enough to require a few extra minutes to bring it back to the same spot in the sky each day, Now here's where the numbers start getting interesting. The Earth's circumference at the equator is approximately 24,901 miles. That entire distance is covered in a single rotation. So if you're standing on the equator right now, you are moving at approximately 1,040 miles per hour. Let that settle for a moment. The speed of sound in air at sea level is around 767 miles per hour. You are moving faster than the speed of sound. Right now, lying completely still, reading or listening to this. But it gets more nuanced than that. The speed of Earth's rotation isn't the same everywhere. It depends entirely on your latitude, how far you are from the equator. The equator traces the largest circle around the Earth. Points near the poles trace much smaller circles. But everyone completes one rotation in the same amount of time. So the farther you are from the equator, the slower your rotational speed. If you're in Miami, roughly 26 degrees north, you're moving at about 980 miles per hour. If you're in New York City, about 40 degrees north, you're moving at roughly 794 miles per hour. If you're in Seattle or the UK, around 47 to 51 degrees north, you're moving somewhere between 650 and 720 miles per hour. If you're in Alaska, closer to 60 degrees north, you're moving at around 520 miles per hour. And if you were standing at the North Pole or the South Pole, you'd be rotating, technically, making one complete turn every 24 hours, but your lateral speed would be essentially zero. You'd just be slowly, almost imperceptibly, spinning in place, everywhere else on Earth. And regardless of latitude, none of this is detectable. Why? Because the atmosphere rotates with the Earth, the oceans rotate with the Earth, every structure and living thing on the surface rotates with the Earth. There is no relative motion between you and your environment. There is no wind created by the spin, because the air is spinning too. The only physical effect of Earth's rotation that we can actually measure, and it's very, very small, is something called the Coriolis effect. It's the subtle deflection of moving objects, like air masses and hurricanes, caused by the Earth rotating beneath them. It's why hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere, but you can't feel the Coriolis effect by lying in your bedroom. It's only measurable over large distances and long durations. In terms of raw sensation, zero, nothing. Complete apparent stillness, that's layer 1. Earth spinning at over 1,000 miles per hour at the equator. And it's just the beginning. Now let's zoom out. While the Earth is spinning on its axis, it is simultaneously orbiting the Sun. This is the motion that gives us our years, the slow annual journey of our planet around its star. The Earth orbits the Sun at an average distance of roughly 93 million miles. Astronomers call this distance 1 astronomical unit, or 1 astronomical unit. It's the fundamental unit of measure for our solar system. The orbit isn't a perfect circle. It's a very slight ellipse. Earth is a little closer to the Sun in early January, around 91.4 million miles, and a little farther away in early July, around 94.5 million miles. The difference is small enough that it doesn't dramatically affect our seasons. Those are caused by Earth's axial tilt, not its orbital distance. The total distance Earth travels in one complete orbit, 1 year, is approximately 584 million miles. 584 million miles. In 1 year, let's calculate the speed. 584 million miles divided by 365.25 days divided by 24 hours per day. The answer, approximately 600 miles per hour. 66,600 miles per hour. Earth's orbital speed around the Sun. Some comparisons. The fastest jet aircraft ever built, the Lockheed State Route 71, Blackbird, had a top speed of around 193 miles per hour. Earth is moving roughly 30 times faster than that. The fastest car ever driven, over 763 miles per hour. Earth is nearly 90 times faster. Even the Voyager 1 spacecraft, Launched in 1977 and now over 23 billion miles from Earth, travels at about 38,000 miles per hour. Earth's orbital speed is nearly twice that. And to make it visceral, every single second, Earth moves approximately 18.5 miles along its orbit. In the time it takes you to blink, roughly a third of a second, Earth has moved about 6 miles. In the time it took you to read that sentence, maybe 3 or 4 seconds, Earth moved over 70 miles, silently, invisibly, completely without your awareness. And here is the beautiful part. Why you feel none of this. It comes back to that same principle. The atmosphere moves with the Earth. Everything on the surface moves with the Earth. There's no wind created by the orbital motion, because the air travels along with us. There's no sensation of speed, because your entire frame of reference, your body, your house, your country, your planet, is all moving together as one system. Additionally, Earth's orbital speed is remarkably constant. It varies by only about 2,000 miles per hour over the entire year, slightly faster in January, slightly slower in July. And that variation happens so gradually over so many months that the resulting acceleration is completely imperceptible. We can calculate it. The centripetal acceleration keeping Earth in its orbit is approximately 0.006 meters per second squared. Gravity, the acceleration you feel pulling you toward the Earth's surface, is 9.8 meters per second squared. Earth's orbital acceleration is roughly 1/600 times weaker than gravity. Your body is so overwhelmed by the sensation of gravity, which you've been calibrated to your entire life, that the orbital acceleration is simply invisible to you. That's layer 2, Earth orbiting the Sun at 600 miles per hour. Let's pause here for just a moment. You're lying still. The room is quiet. And so far, we've established that you're spinning at roughly 1,000 miles per hour and orbiting at roughly 66,000 miles per hour. That alone is extraordinary. And we haven't even left the solar system yet. I want you to feel, just briefly, what that actually means, not intellectually. Feel it in your body. The floor beneath you is moving. Right now, the house or apartment around you is moving. The city you're in is moving. The continent under you is moving. The entire planet is spinning and hurtling through space. And you feel nothing. Take a breath. The universe is doing something remarkable right now. It is carrying you. You don't have to do anything. You don't have to hold on. You don't have to steer. The cosmos has been carrying you since the moment you were born. Let that be the background of everything else tonight. Now let's keep going. Here's where things start to feel genuinely surreal. You might have assumed, most people do, that while Earth is moving, the sun is fixed. That the sun is the anchor, the still point at the center of our solar system, everything else orbiting around it. But the sun is not still. The sun is moving, and it's taking everything with it. All 8 planets, all their moons, the asteroid belt, the Kuiper belt, comets, dust, everything. The entire solar system is a kind of cosmic caravan, following the sun through the galaxy. Our galaxy, the Milky Way, is a barred spiral galaxy containing somewhere between 100 and 400 billion stars. It's shaped roughly like a flat disk, with spiral arms curling outward from a central bar-shaped core. If you could look at it from above, it would look something like a slow-motion pinwheel. The sun sits in one of those outer spiral arms, the Orion arm, about 26,000 light-years from the center of the galaxy. To put that in miles, roughly 153 quadrillion miles from the galactic core, and the sun is orbiting that core, traveling in a vast, nearly circular path around the galactic center, completing one full orbit approximately every 225 to 250 million years. Astronomers call this period a galactic year, or sometimes a cosmic year. The last time the sun was in this exact position in its galactic orbit, dinosaurs were just beginning to dominate the Earth. The Triassic period had just ended. The Jurassic had barely begun. Before that, multicellular life was just becoming established on Earth. One galactic year before that, Earth itself didn't exist yet. We are currently about 20 galactic years old as a solar system. Now, the speed. The Sun is moving through the galaxy at approximately 490,000 miles per hour, nearly 500,000 miles per hour. To put that alongside our previous numbers, Earth's rotational speed at equator, approximately 1.04 mph. Earth's orbital speed around Sun, approximately 66,600 miles per hour. Sun's orbital speed around the galaxy, approximately 490,000 mph. The Sun is moving 7 times faster than Earth orbits it. It is 220 times faster than Earth's rotation. Every second, the Sun travels about 136 miles through the galaxy. In the time it takes you to blink, the Sun, and you with it, has traveled several miles through galactic space, and you feel absolutely nothing. The reason is the same as before. The entire solar system is moving together as a unit. Earth is moving with the Sun. The Moon is moving with Earth. All the planets travel in concert. There's no relative motion within the system to detect, and the vast emptiness of space provides no resistance. There's one more layer to this, though. The Sun isn't moving in a straight line. It's orbiting, which means it's constantly changing direction. And changing direction is a form of acceleration. But the scale of the galaxy is so incomprehensibly vast that the curve of the Sun's orbit is barely a curve at all from our perspective. The centripetal acceleration keeping the Sun in its galactic orbit is roughly 2 times 10 meters per second squared. That number is so small, it's almost meaningless to say out loud. It is approximately 50 billion times weaker than Earth's gravity. Completely, entirely, utterly imperceptible. That's layer 3, the Sun dragging the entire solar system and you through the Milky Way at 490,000 miles per hour. We've talked about Earth spinning, Earth orbiting, the Sun moving through the galaxy. But what about the galaxy itself? Is the Milky Way standing still? No, not even close. The Milky Way is moving through space, and this is where the question gets philosophically complicated. Because to say something is moving, you need a reference point. You need something to compare it against. In everyday life, we compare motion to the ground, or to another car, or to a building. But in the context of the universe at large, what do you compare a galaxy's motion to? There's no cosmic signpost, no universal 0 miles per hour, no fixed point in space that's truly standing still. Everything is moving relative to everything else, so scientists had to get creative. They found the most useful reference frame in the universe, one that is, in a very specific sense, the closest thing we have to a universal background. That reference frame is called the asterisk cosmic microwave background asterisk, or the CMB. The cosmic microwave background is the oldest light in the universe. It's the afterglow of the Big Bang. In the very early universe, the first few 100,000 years, space was so hot and dense that light couldn't travel freely. Photons were constantly being absorbed and re-emitted, bouncing around in an opaque fog of plasma. Then, approximately 380,000 years after the Big Bang, the universe had expanded and cooled enough that electrons and protons could combine to form neutral hydrogen atoms for the first time. The fog cleared. Light was suddenly free to travel. And that light has been traveling ever since. For nearly 13.8 billion years, it has been streaming through the expanding universe in every direction. It has been stretched by cosmic expansion until it has cooled to a temperature of just 2.7 degrees above absolute zero, barely detectable as microwaves. Today, it fills the entire observable universe from every direction. No matter where you point a sensitive radio telescope, you detect this faint, ancient glow. It is almost perfectly uniform in every direction. Almost. There is a very slight, almost impossibly faint, temperature variation across the sky. One side of the sky, in the direction of the constellation Leo, is microscopically warmer. The opposite side, toward the constellation Aquarius, is microscopically cooler. The difference is only about 0.0033 degrees Kelvin. That is a difference of 33/10,000ths of a degree. But it is measurable. And it tells us something profound. It tells us we are moving relative to the CMB. Here's why. When you move through a medium, even a medium as diffuse and ancient as the cosmic microwave background, the waves in front of you get slightly compressed, blue shifted, and the waves behind you get slightly stretched, red shifted. Compressed waves have slightly more energy, which means they register as slightly warmer. Stretched waves have slightly less energy, which registers as slightly cooler. This is the Doppler effect, the same phenomenon that makes a passing ambulance's siren pitch higher as it approaches and lower as it recedes. By measuring the exact temperature difference of the CMB across the sky, scientists can precisely calculate our speed relative to this cosmic background. And the answer is 1,342,000 miles per hour. 1,342,000 miles per hour. That is the speed of the Milky Way galaxy, and by extension, you through the cosmos, as measured against the most fundamental reference frame in the universe. Every second, the Milky Way moves approximately 373 miles relative to the CMB. Every minute, over 22,000 miles. Every hour, over 1.3 million miles. In an 8-hour night of sleep, 10.7 million miles. You traveled over 10 million miles last night. While you were dreaming, while your body lay perfectly still in bed, you didn't feel a thing. Here is where the story gets even stranger and even more beautiful. The Milky Way's motion relative to the CMB isn't random. It isn't drifting aimlessly through empty space. It's being pulled by gravity towards something about 150 million light-years away from us, in the direction of the constellations Hydra and Centaurus. There is a colossal concentration of mass. Astronomers call it the Great Attractor. It isn't a single object. It isn't one black hole or one giant galaxy. It's a massive gravitational anomaly, an enormous overdensity of matter, possibly a supercluster of galaxies containing the mass of tens of thousands of Milky Ways. And it is pulling on us, on our galaxy, on thousands of other galaxies in our local region of the universe. Everything in a vast cosmic neighborhood, including the Milky Way, is slowly, inexorably falling toward the Great Attractor. Falling might sound alarming, but gravitational motion always looks like falling when you describe it plainly. When Earth orbits the Sun, it's technically falling toward the Sun, but moving sideways fast enough to keep missing it. The Moon is falling toward the Earth right now. It just keeps missing. The Milky Way is falling toward the Great Attractor. Whether we'll simply pass through it, orbit it, or merge with whatever is there, that depends on dynamics that will play out over billions of years. But wait, it gets bigger, because the Great Attractor itself is being pulled by something even larger. Beyond it, about 400 million light-years away, is the Shapley supercluster, one of the largest concentrations of mass in the observable universe. It contains the mass of tens of thousands of galaxies, and it appears to be a more fundamental gravitational driver of our entire local supercluster, possibly the anchor pulling the Great Attractor and everything around it in a specific direction. And beyond the Shapley supercluster, even larger structures, vast filaments of galaxies, cosmic walls stretching for hundreds of millions of light-years. Supervoids, the cosmic web. The universe is not a uniform, evenly distributed collection of matter. It is a staggering architecture of threads and sheets and clusters and emptiness, all gravitationally influencing everything else. And everything in it is in motion. We are embedded in a vast, flowing river of cosmic motion, pulled by gravity, stretched by expansion, carried along by forces that operated on scales almost impossible to imagine. At this point, you might want to just add up all those speeds and get a final number. Let's try. Earth's rotation at equator, approximately 104 OMPH. Earth's orbit around the Sun, approximately 600 miles per hour. Sun's orbit around the Milky Way, approximately 490,000 mph. Milky Way's motion relative to CMB, approximately 1,342,000 mph. If you simply add those numbers, 1,899,640 miles per hour, roughly 1.9 million miles per hour. But here's the honest complication. You can't just add them like that. These motions are not all in the same direction. They're vectors. Each one has both a magnitude, speed, and a direction. And those directions are different. Earth's rotational axis is tilted 23.5 degrees relative to its orbital plane. The plane of Earth's orbit is inclined relative to the plane of the galactic disk. The Milky Way's motion relative to the CMB is in yet another direction, not aligned with the galactic plane. To get the true combined speed, you'd need to do vector addition, treating each motion as an arrow in 3D space, combining them mathematically. The result changes depending on where you are on Earth, what time of year it is, even what time of day it is, because Earth's rotation shifts your direction every hour. The cosmic motion component, dominated by the Milky Way's motion relative to the CMB, stays essentially constant at over 1 million miles per hour. The smaller components, rotation, orbit, galactic orbit, add some amount depending on their current directional relationship to that dominant cosmic motion. The bottom line, your total speed through the cosmos is comfortably over 1 million miles per hour at all times. On a good day, when the vectors align in a cooperative way, potentially approaching 1.5 to 1.9 million miles per hour, you are a multi-million mile per hour traveler, every moment of your life. So let's address this directly now. In full. Why does none of this produce any sensation whatsoever? The answer is rooted in several beautifully connected principles of physics. Principle 1. Constant velocity is inherently undetectable. This is the bedrock of Galilean and Einsteinian relativity. If you are moving at a constant speed in a constant direction, there is no physical experiment, no sensation, no measurement you can make from within your reference frame that can detect that you're moving. Think about this carefully. It's not that your senses are too weak or too primitive. It's that there is literally nothing to detect. Motion at constant velocity produces no force, no push, no pull, no sensation. There is nothing there to feel. The laws of physics work identically whether you're at rest or moving at 1 million miles per hour, as long as that speed is constant and the direction is constant. This is why being in a smoothly cruising airplane feels indistinguishable from sitting in a room on the ground. Not because your senses are fooled, but because physically they are the same situation. Principle 2, what you actually feel is acceleration, not speed. Your body has exquisite sensitivity to acceleration, to changes in velocity. This is what your inner ear detects. This is what creates the sensation of being pushed back in your seat when a car speeds up. When a car accelerates from 0 to 60 miles per hour in 4 seconds, you feel that because the rate of change is significant relative to your body's weight. Earth's rotation produces a centripetal acceleration at the equator of 0.034 meters per second squared. Compare that to gravity, 9.8 meters per second squared. Rotation's effect is nearly 290 times smaller than gravity, completely lost in the noise. Earth's orbital centripetal acceleration is even smaller, about 0.006 meters per second squared. Roughly 1/600 times smaller than gravity. The Sun's galactic centripetal acceleration, approximately 2 times 10 meters per second squared, literally 50 billion times smaller than gravity. All of these cosmic accelerations are so vanishingly tiny compared to the gravitational field you're sitting in, that they're not just hard to detect, they're physically impossible to detect with any biological sense organ. Principle 3. There is no medium pushing back against us. When you drive a car with the window down, you feel the wind. That wind is the air resisting your passage through it. Friction, drag, resistance. When Earth moves through space, it is moving through a near-perfect vacuum. There is no air in space. There is almost nothing. Space is not entirely empty. There are a few hydrogen atoms per cc in the interstellar medium. There are cosmic rays. There is a very thin solar wind. but the density is so incomprehensibly low that at any speed a planet might travel, the resulting drag is negligibly, unmeasurably small. There is no cosmic wind pressing against your face. There is no resistance slowing us down. There is nothing to feel. We move through the void, and the void offers no feedback. Principle 4. Everything in our reference frame moves with us. The Earth's atmosphere moves with Earth. The air in your room moves with Earth. The house moves with Earth. You move with Earth. There is no relative motion between you and anything in your immediate environment because of this planetary motion. Your senses can only detect relative motion, and there is none. This is perhaps the most important principle of all. You are not just a person moving through space. You are a person embedded in a moving system, a system so large and so unified that every single thing you could possibly measure yourself against is moving with you. It would be like trying to detect that you're in a moving car by watching the other passengers. They're all moving with you. Nothing shifts. Nothing changes. The universe moves with you. You move with the universe, and so you feel nothing. Part 11. The expanding universe, the strangest motion of all. There's one more layer of motion we haven't discussed yet, and it's the strangest one. Not just strange, it's a fundamentally different kind of motion than everything we've talked about so far. The universe itself is expanding. Not the stuff in the universe, the space itself. The fabric of space is stretching. And this isn't a motion through space. This is a motion of space. To understand what this means, think of the classic analogy. Imagine a balloon with dots drawn on its surface. When you blow up the balloon, the dots move apart, but none of the dots are moving across the surface of the balloon. The surface itself is expanding and carrying the dots with it. That's what's happening in the universe. The galaxies are the dots. Space is the balloon. The galaxies aren't moving through space. Space is growing between them. The farther apart two galaxies are, the more space there is between them, and so the faster the expansion carries them apart. This relationship is described by Hubble's law, formulated by astronomer Edwin Hubble in 1929, after he discovered that distant galaxies were receding from us in a pattern directly proportional to their distance. The current value of the Hubble constant is approximately 46 miles per second per megaparsec. A megaparsec is 3.26 million light-years. What that means in practical terms: a galaxy 100 million light-years away is being carried away from us at roughly 1/400 miles per second, about 5 million miles per hour. A galaxy 1 billion light-years away, about 14,000 miles per second to 50 million miles per hour. A galaxy 10 billion light-years away, about 140,000 miles per second, over 500 million miles per hour. And at a certain distance, roughly 14 billion light-years galaxies are being carried away from us at the speed of light. Beyond that distance, galaxies are receding faster than light. And here's the crucial thing. This doesn't violate Einstein's theory of relativity. Nothing is moving through space faster than light, but space itself can expand at any rate. There's no speed limit on the expansion of space. The boundary where recession velocity equals the speed of light is called the cosmic horizon, the edge of the observable universe. Anything beyond that horizon is receding so fast that its light will never reach us, no matter how long we wait. Not because the light isn't traveling, it is at the full speed of light, but because the space between us and those distant galaxies is expanding faster than the light can cross it. The observable universe, the sphere of space from which light can ever reach us, has a radius of about 46.5 billion light-years. Beyond that infinite universe, possibly, we simply can't see it. We can't reach it. It is, in the most literal possible sense, beyond our cosmic horizon. And that universe keeps growing. The edge of what we can see recedes a little more each year. Not because we're looking farther, but because expansion is constantly adding new space, just within range. We are in a bubble of light, and the bubble's edges are forever out of reach. Everything we've talked about so far has been about the present. But the natural next question is, where does all this motion lead? Where is the universe taking us? The collision with Andromeda. Our nearest large galactic neighbor is the Andromeda Galaxy, designated M31. It's roughly 2.537 million light-years away. Close enough that on a very dark night, far from city lights, you can actually see it with the naked eye. It's the farthest object visible to the unaided human eye. A faint, elongated smudge in the northern sky. And Andromeda is coming toward us. Based on careful measurements of its motion across the sky and its approach velocity, astronomers have determined that Andromeda is falling toward the Milky Way at roughly 68 miles per second, approximately 250,000 miles per hour. In about 4 billion years, the two galaxies will collide. Now, collision is a misleading word. When galaxies collide, individual stars don't actually crash into each other. The distances between stars are so vast that direct stellar collisions would be extraordinarily rare events. Think of it this way. If our sun were the size of a marble, the nearest star system, Alpha Centauri, would be about 30 miles away. Two galaxies merging would be like two enormous, incredibly sparse swarms of marbles passing through each other. Mostly empty space encountering mostly empty space. What does happen in galactic collisions is dramatic in other ways. The gravitational forces distort and reshape both galaxies. Stars get flung into new orbits. Some are hurled out into intergalactic space. Vast clouds of gas are compressed, triggering enormous bursts of star formation, stellar nurseries blazing to life across the merged system. Both galactic cores, with their supermassive black holes, orbit each other and eventually merge into a single, larger black hole. The entire process takes hundreds of millions of years. Simulations show the two galaxies passing through each other once, separating briefly, then falling back together and fully merging. After roughly 6 billion years from now, the combined structure will settle into a new shape, likely a large elliptical galaxy, no longer spiral, a great cloud of stars with no defined disk or arms. Some astronomers have affectionately nicknamed this future galaxy *Milkomeda* or *Milkdromeda. Where will the sun be during all this? Almost certainly still existing, stars of the sun's size and type live for about 10 billion years, and the sun is currently about 4.6 billion years old. It likely has another 5 billion years of main sequence life ahead. It will probably be flung into a new region of the merged galaxy, but it will survive. Earth? By the time the collision begins, the sun will already have brightened significantly enough that Earth's surface will be too hot to support life as we know it. But the planet itself will likely persist, a scorched rock with a very different story. The long-term fate of the universe. Now let's look further. In 1998, one of the most stunning discoveries in the history of science was made. The expansion of the universe is not slowing down, it's speeding up. Two teams of astronomers, studying distant supernovae as cosmological distance markers, independently found that supernovae far away were dimmer than expected, farther than they should have been if the expansion were simply coasting or decelerating. The universe wasn't just expanding, it was accelerating its expansion. They received the Nobel Prize in Physics in 2011 for this discovery. The force driving this acceleration is unknown. Astronomers call it dark energy, not because it's dark in the optical sense, but because we don't know what it is. It appears to be a property of space itself, an energy inherent in the vacuum that acts as a kind of anti-gravity, pushing the expansion faster over time. Dark energy accounts for approximately 68% of the total energy content of the observable universe. Dark matter makes up about 27%. The ordinary matter we can see, stars, planets, gas, dust, everything made of atoms, makes up only about 5%. We are a thin layer of froth on a vast, dark ocean we don't understand. The implications of this accelerating expansion are profound. In the far future, on timescales of tens of billions of years, galaxies in the local group, our small cluster of galaxies, which includes the Milky Way and Andromeda, will have merged. But galaxies beyond the local group will be receding ever faster, pushed by dark energy beyond our cosmic horizon. The cosmic horizon will recede. More and more of the universe will become forever unreachable to us. Future civilizations, if they exist, will have a smaller and smaller observable universe to study. On even longer time scales, hundreds of billions of years, the last stars will burn out. No more nuclear fusion. The universe will grow dark and cold. Black holes will dominate. And then, over enormous periods of time, possibly 10 to the power of 100 years or longer, even black holes will slowly evaporate via Hawking radiation, emitting their mass as faint thermal radiation. Eventually, in the most distant imaginable future, the universe reaches what physicists call maximum entropy. No gradients, no useful energy, no complexity, no motion that can do work. A cold, still dark fog of the most diffuse particles imaginable. This is sometimes called the heat death of the universe, or the Big Freeze. But this is so incomprehensibly far in the future that it should cause you no worry tonight. Right now, the universe is young, the universe is rich. Stars are burning, galaxies are colliding, planets are forming, life is happening, and you are part of it. All of this, the speeds, the scales, the distances, the timelines, adds up to a kind of philosophical statement about our place in the cosmos. We are not at the center. This was not always obvious. For most of human history, it was assumed, felt, deeply felt, that Earth was the center of the universe. The sun went around us. The stars were a ceiling placed above us. We were the point of it all. In the 1540s, a Polish astronomer named Nicolaus Copernicus proposed something that upended this understanding. He suggested that the Earth orbited the sun, not the other way around, that we were not the center. This idea, later confirmed and extended by Galileo, Kepler, and Newton, was not just a scientific revision, it was a philosophical earthquake. The Copernican principle, as it's now called, is the idea that Earth does not occupy a special or privileged position in the universe. Subsequent centuries only confirmed how correct this was. The sun is not at the center of the galaxy. The Milky Way is not at the center of the universe. There is no center of the universe. Every point in the universe sees the same expansion happening around it. We are one planet, orbiting one star, in one galaxy, among hundreds of billions of galaxies, in a universe of staggering scale and indifferent grandeur. This could feel deflating. For a long time in the history of science, it was framed that way. We are insignificant. We are nothing. A pale blue dot in a vast cosmic wilderness. Carl Sagan said it beautifully when he described the famous Voyager photograph taken from 3.7 billion miles away, Earth as a tiny, barely visible speck of light. He said, "Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves." A sobering thought. A humbling thought. But Sagan also said something else, something that turns the humility into wonder rather than despair. We are a way for the cosmos to know itself. Think about what that means. The universe has been expanding for 13.8 billion years. Stars have burned and died. Supernovae have scattered elements across the galaxy. Those elements coalesced into planets. On at least one of those planets, probably many more, those elements organized into life, and eventually into minds. Minds that look up, that wonder, that ask, how old is this? How large is it? How fast are we moving? You are made of atoms forged in the hearts of stars that lived and died before the sun existed. Your iron was hammered out in a supernova. Your carbon was cooked in stellar fusion. Your hydrogen has been here since the first minutes after the Big Bang. You are 13.8 billion years old in a very real sense. You are star stuff, as Sagan said, ancient beyond imagination. And you are aware of it. That awareness, that capacity to ask the question, to build the telescopes, to measure the temperature of ancient light and calculate the speed of a galaxy is, as far as we know, extraordinary in this universe. The universe is vast and old, and you are small and brief. But you are the part of the universe that gets to wonder about itself. That is not nothing. That is, perhaps, everything. Before we close, let's compile everything we've talked about. Not to overwhelm, but to let it land. Earth's rotation at the equator, approximately 1,040 miles per hour. Faster than the speed of sound, happening right now as you lie still. Earth's orbit around the sun, approximately 600 miles per hour. 30 times faster than the fastest jet ever built. Every second, you've moved 18.5 miles. Sun's orbit around the Milky Way, approximately 490,000 miles per hour. 500,000 miles per hour. The entire solar system, carried in a vast galactic circuit. Milky Way's motion relative to the cosmic microwave background, approximately 1,342,000 miles per hour, over 1,000,000 miles per hour. This is the dominant cosmic speed. This is the number that matters most. Total combined magnitude, over 1,000,000 miles per hour. Potentially approaching 1.5 to 1.9 million miles per hour, depending on directional alignment of the component vectors. Every second of your life you have been traveling at these speeds. Every night you've slept, every meal you've eaten, every conversation you've had, every moment of joy or grief, or boredom, or wonder, all of it has happened while you were hurtling through space at extraordinary velocity. And through all of it, you felt nothing. The universe carried you in silence. I want to end tonight with a thought that I find more comforting than almost anything else I know about physics. You cannot control any of this. Not the spin of the Earth. Not the orbital path around the Sun. Not the vast galactic journey. Not the pull of the great attractor. Not the expansion of the universe. These forces operated long before you were born. They will continue long after. They are, in the most complete sense possible, beyond your influence. And yet, they are working. Every second, the cosmos is carrying out this elaborate, precise, delicate choreography. The Earth maintains its orbit to within fractions of a percent. The Sun follows its galactic path with gravitational precision. The CMB fills the sky with its ancient, gentle warmth. Everything is moving, everything is working, everything is going where it is supposed to go. And you are part of this system. You are embedded in it, carried by it. Tonight, when you close your eyes, the Earth will continue to spin. The Sun will continue its galactic journey. The Milky Way will continue racing through the cosmos at over 1,000,000 miles per hour. You don't have to do anything. The universe has you. You have been in motion since the moment you were born. Cosmic motion, vast and ancient and impossibly fast. And you will be in motion every moment until your last. Moving, and always feeling, from the inside, like perfect stillness. Outro. Sleep well, traveler. This is the last thing I want to leave you with tonight. Somewhere in the direction of Leo, painted faintly across the sky, the ancient light of the cosmic microwave background is coming toward us, slightly warmer than the sky on the other side. A tiny temperature difference, a quiet whisper from the Big Bang, telling us which way we're going. 150 million light years from here, something vast and massive is gently, patiently pulling us toward it. 4 billion years from now, Andromeda will fill our sky. 13.8 billion years ago, everything that would ever exist exploded outward from a single point of infinite density and began the journey that eventually, somehow, improbably produced you. And tonight, you are here, in this room, moving at over 1,000,000 miles per hour, feeling completely still. Take a breath, let your body relax. The cosmos has been carrying you for every second of your life. It will keep carrying you tonight. You don't have to hold on, just let go. Sleep well, traveler. The universe knows where it's going, and it's taking you with it. If you enjoyed this exploration of our ever-moving universe, please like the video and subscribe for more relaxing science documentaries. I'd also love to hear your thoughts in the comments. What fact about motion in the universe surprised you the most? Thank you for spending this time exploring the cosmos with me. Sleep well, and I'll see you in the next journey through science and space.